Number 3. So let's see. What does it say? A friend catches the ball in problem number 2. Okay. I hate problems like this because it's a deceptive way to try and get me to do problem number 2. I don't want to do problem number 2. You didn't ask about problem number 2. It says a friend catches the ball in problem number 2 at the bottom of the drive and rolls it back up the drive towards you. It is traveling at 0.5 meters per second when the ball makes it to you. How fast do they roll the ball up the driveway? Okay. We're going to need something from problem number 2, I think, to do problem number 3. But let me start by saying it's always in your best interest, if you can, to try and draw a picture of what it is you're trying to talk about. So please consider drawing these out. In the next unit, I'll be requiring that you draw them out. And there's a lot of reasons for that, but the biggest reason is getting positive and negative to work out for you, for values that are vectors, can be difficult for students, especially as they're first starting out. Just draw the whole thing out so we all kind of know. So it says a friend catches the ball in problem number 2 at the bottom of the drive and rolls it back up the drive towards you. So I'm assuming that this is the initial velocity of the ball. And it's traveling 0.5 meters per second when the ball makes it to you. So you're up here someplace, and the ball makes it to you. It's traveling 0.5 meters per second. And we know that this distance is 4 meters. And it made it down the ramp in 2 seconds. So this is all the information we have been given. Now, the first thing I will note, if you want a picture to be of use to you, one of the things you should probably do is identify what direction is going to be positive and what direction is going to be negative. I'll require this in other units. It's good practice now, because you're also then telling the grader what direction is positive and what direction is negative, and they'll understand what you're trying to get at. So would you like to the right to be positive or to the left to be positive? Wow, that sounded right down the middle. And I don't care. We just need to be consistent. So I'm going to make right positive and left negative. Now, the truth is, we don't have enough information. Based on what I've written down, delta x is positive 4 meters. The initial velocity is unknown, but the final velocity is positive 0.5 meters per second. That's only 2 pieces of information. So without it, we can't solve the problem. It's expecting you to get something from question number 2. Yes, sir?
Acceleration?
We would have to have, I think the acceleration is probably the right bet, because it's the same drive, which means the same inclination, and it's the inclination that determined what the acceleration was. So I think we need the acceleration from number 2. Do I need to work number 2 to get it, or do you guys already have it? Go ahead. 2 meters per second squared? Well, I'm just going to say 2 for a minute. Does everybody agree with the size of that number? All right. Can we also agree that the acceleration has to be this way on the ramp? Is that good for everybody? And it's 2 meters per second squared. So if I interpret that right, in this problem, I would say negative. Now, the reason I'm being so cagey about positive and negative isn't because I don't trust you guys, but half of you said that to the left was negative, and half of you said to the right was negative. Right? When I asked, what direction should I make positive, you guys split down the middle. So I want to be careful when I talk about direction for anything. We have established that down the ramp is negative, and the acceleration has to be down the ramp, so I made it negative. Had you guys, or had I, decided to make down the ramp positive, then I'd have to flip all these numbers signs. You just need to be consistent in your application. So now all I need is this. I think that's all it wants. So of the available possible things I could use, the one I'm going to use, v squared minus v naught squared equals 2a delta x. So 0.5 squared minus v naught squared equals 2 times negative 2 times 4. So negative 8 and 0.25 minus v naught squared. So I'm going to subtract the 0.25 from both sides, and I'll get negative v naught squared equals negative 8.25. Yeah. It should be negative 16. Thank you. Thus, negative 16.25. Strip off the negative signs and take the root. So V naught's going to be a little greater than 4 meters per second. Right, square root of 16 is 4, so what, 4.1? Right? Yeah?
Question 2 and 3, should you make like the positive and negative same for both questions, or it doesn't matter? Like, just because it says like question 3, go back to question 2?
It doesn't matter.
It doesn't matter?
Mm-hmm. But be careful. This is not the right answer. The right answer is to say plus or minus. Your whole problem would have been identical if you had done it this way, except that the negatives and positives would have been reversed. But at the end, you would have to choose the right one of these, right? This particular equation can't tell you the direction of a velocity if that's what you're solving for. You have to choose the correct direction for the velocity. Now, we know that the correct answer should be the one that pushes it up the ramp. But if you had switched your positive and negative, you would have had to have chosen negative 4 meters per second as your velocity to indicate it's up the ramp, or said as your answer 4 meters per second up the ramp. If you want to really drive the answer home. Follow what I'm saying? Hope so. Alrighty. We've done number 7 before. Number 7 is the police officer question. Just written with a little difference, not very much actually, but enough, I guess, to get us started. To do this question, again, I'm going to draw a picture. A cyclist traveling at a constant 10 meters per second passes another doing 5 meters per second. The second cyclist, not wanting to be beat, accelerates constantly at 1 meters per second squared until they eventually catch the first cyclist. How long do they have to maintain this acceleration? How fast are they going when they reach the first cyclist? And how far have they traveled? Can you use a website like Desmos, your calculator, or your phone to create a graph that would demonstrate this? So we can, and I will if you'd like. I used Desmos in the last class period to do number 9, but we could use it right here. And if you have a TI, take it out, because most of you should know how to use a TI to do this. But let's go ahead and start this problem. First, I believe that this person, this cyclist, number 2, must prefer they, them pronouns, because that whole thing refers to just the second cyclist. They are the only one accelerating. Does everybody understand why that has to be true? I'm not convinced. If both cyclists accelerate at 1 meter per second squared, then the second cyclist can't catch the first. So only one is accelerating. Fair enough? So cyclist number 1, again, draw a picture, and cyclist number 2. Cyclist number 1 is already traveling quite fast at 10 meters per second. Just over 20 miles an hour. Cyclist number 2 is pedaling at 5 meters per second. And this represents the origin. This is where the two cyclists are together. Cyclist number 2 accelerates at this moment at 1 meter per second squared. And I assume it makes reasonable sense they accelerate in the direction of motion to make them go faster. They're not trying to slow down. So that at some point in the future, at some location X, both cyclists are together again. This one's still traveling 10 meters per second, but I bet this one traveling faster. A picture? Good? A reminder, delta x equals x minus x naught. Are we good? I'm doing this as like some foreshadowing for question number 8. Cyclist 1, cyclist 2. Delta x, v naught, v a t. And again, you had this problem in class, so you could have looked at it. Here we go. I'm going to break apart the delta x and write the delta x as x minus 0 for this guy. I have a reason why I want to do this that won't be obvious in this problem. Initial velocity, 10 meters per second. Final velocity, 10 meters per second. Acceleration, 0. I'm going to make this direction the positive direction, and therefore all of those values are positive. That doesn't tell me very much, but because the acceleration is 0, I can make the statement that the only relationship that exists is x minus 0 equals 10t. We good to keep going? All right, cyclist number 2. Let's see. X minus 0. Again, I'm going to break out the delta and make it x minus x naught. Initial velocity 5, and it's positive. Final velocity unknown, but the acceleration is 1 meter per second squared. Seems to me I could bring these things together too. If I ignore the final velocity, I could write x minus 0 equals 1/2 a t squared plus v naught times t. Now, the reason this is important is that both cyclists make it to the same place at the same time, just like the police officer one. So I could recognize that this relationship and this relationship can be brought together. They come to the same place at the same moment in time. So let's do a little algebra. That's all this is. I'll say place this over for x. And I'll get 10t equals 0.5 t squared plus 5t. Or 0 equals 0.5 t squared plus, not plus, minus 5t. Seems to me I can get two values for t here. T equals 0 and t equals 10 seconds. And remember, factor out the t. Don't divide by it because it's 0. You can't divide by 0. You should have two answers for a quadratic in most cases. Even if they don't seem to make sense, you should contemplate them. In this case, the first one, the first 0, is when they were first lined up. At that moment, their positions were the same at time 0. And then apparently they'll be the same again at t equals 10 seconds. Now, this is not the answer. It didn't ask when. It asked where and how fast. So I think the best way to get where is right there. They meet again at the 100-meter mark. But if I want how fast, well, then I might have to go back to this to figure out how fast he's going and choose a different relationship. And I will choose v squared minus v naught squared equals 2a delta x, or v minus 5 squared equals 2 times 1 times 100. That's 200 plus 25. V equals 225. And is the root of that 15? So, is that right? I think so. So 15 meters per second. That's exceptionally quick. I cycle regularly. I can't get 35 or 34 miles an hour, which is how fast this guy would be cycling. But cycling 10 meters per second is no slouch. That's around 21 miles an hour, which to me is fast. I can do it, but not for very long. So 30-something miles an hour, well, I'm sure there's guys who can do it, but that's why I will not probably ever, do the Tour de France or anything like that. Just cycling for exercise, as opposed to being, an award-winning cyclist. Anybody else cycle out there? Well, it's excellent, healthy, low impact to the joints. All good things. I'm old. Good enough for this one? Very thorough, nice and slow, deliberate. So I guess that means we have to do, wait. So let's talk about number 8. I like number 8 quite a bit. This is the train question, right? So let's talk about number 8. 2 trains are traveling towards each other, both traveling at 20 meters per second. They are both 1,000 meters apart. Both hit the brakes, but one train's brakes fail, while the others are only good enough to provide an acceleration of 0.5 meters per second squared. Where do the trains collide? Excellent question. Where do the trains collide? I'm going to draw a picture. So, again, I would encourage you guys to draw a picture. Train number 1. Train number 2. And let's see, 20? Yeah. All right, so here we go. Train number 1, train number 2. There's a number of ways to attack this problem. In prior years, I probably would have attacked it differently than I'm attacking it now. I think the way I'm going to attack it this year makes more sense and is more consistent with what we've done so far. One way you could have attacked this problem from the standpoint of, I would say, I don't want to use the word novice, but a way that if you're not careful can get you into trouble is to assume they meet someplace and say that this one travels a distance X and this one travels a distance 1,000 minus X. That's fair. That works. But I want to do this different. So this is how I might have talked to you guys about doing it last year. The advantage of doing it this way is that you can treat both trains as if they're traveling in a positive direction. And so there are some advantages to doing it like this. But I want you to be more robust in your ability to use direction more carefully. So first, is the train on the right or the train on the left the one that's slowing down? It doesn't matter. Pick one. Raise your hand if you want left. Wow, it's none of you. Okay, so the right train is slowing down at 0.5 meters per second squared. I directed the acceleration to the right because that train is moving to the left, so the acceleration must be to the right to slow the train down. Agreed? All right. What direction would you like to be positive, left or right? You guys are hilarious. So clearly it doesn't matter to any of you because I got both lefts and rights. Right? Okay, so we'll make the right positive. Fine. Now, here's something that's a little bit different. The trains are on a number line. So I'm going to treat one train as if it's at the origin and one train as if it's at a point 1,000 meters away from the origin. So which train is at the origin from the way I've drawn this so far? The left train or the right train? It would make more sense from your training on number lines to make the left one because you've always believed that to the right is the way a number line is positive. I don't know who made you think that. Probably some 3rd or 4th grade teacher. But since it's been pretty well ingrained in you, that would mean that this train is at the positive 1,000 meter mark. Good enough? So, train number 1, delta x, v naught, VAT, and delta x, v naught, VAT. Bless you. So the real question is, I think we've done a pretty good job laying out this problem. The only thing I want to point out is I'm not going to use delta x. I'm going to use what delta x means. So I'm going to say delta x equals x minus x naught for both. So here we go. Train on the left. X minus 0. Initial velocity, positive 20 meters per second. Final velocity, initial velocity, positive 20 meters per second. Initial velocity, unknown. Acceleration, 0. So actually, I guess we do know the final velocity is 20 meters per second. Time, unknown. There, we've got train 1. I'd probably argue that we could write out x minus 0 equals 20t and set that aside. Ready for train number 2? Excellent. X minus 1,000 meters. V naught, negative 20 meters per second, right? It's traveling to the left. So I need to make sure I choose the appropriate sign for my velocity. My picture makes it clear, which is why I would encourage you to use a picture like this. Final velocity unknown, but acceleration positive 0.5 meters per second squared. Don't know the time, but I think I can put together a displacement versus time function. Because I already have a displacement versus time function for train 1, I think a displacement versus time function for train 2 would make reasonable sense. Yay! Is that what you guys got? That's what I got. Now, to me, the problem is done. I see no point in going on. Because we've done all the physics. Everything left here is just a math problem, which is not that interesting to me. We can bring, Mr. Brashear, Ms. Smith in here and say, hey, here's math. Do some math. But I know you students are never satisfied unless you have an answer in front of you. Besides, I want to prove something. That you guys are, often deceived on your own. So let's figure out the answer, shall we? Now, Desmos would give us the answer. Your calculator would give you the answer. I'll show you that second. I want to do the problem first. So here we go. I'm going to do the obvious substitution. Obvious substitution. The final position has to be somewhere between the two trains. So this X actually marks the spot of where they're going to end up, somewhere between the two trains. And they'll be there at the same moment in time. So I'm going to eliminate X and find T. It's a lot harder to eliminate T in this one and find X. So I will have 20t minus 1,000 equals 0.25. Oh, I forgot the t squared there. Nobody pointed it out. Thank you. You didn't point out my mistake, so allow me to point it out for you. I forgot to put a t squared right there. I didn't do the right equation, but I fixed my mistake. Thank you for not pointing it out, though, and letting me do it myself. So, This is not very interesting to me, but we're going to work it out anyways. We need t, because I want to prove something. So I'm going to get everything to one side. 0 equals 0.25 t squared minus 40t plus 1,000. I don't know if this factors or not. I could multiply everything by 4 to at least get it all in integers, but I'm just going to assume it doesn't factor and do the quadratic formula. So t equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. And you guys, I know, love your calculators, but I always find calculators to be somewhat demeaning and deceitful. Meaning, you guys will punch stuff in there and get the wrong answer all the time. And I've never been particularly happy with that. Like, you just punch numbers, and whatever the calculator tells you, you accept that as the truth. But I'm finding that for the most part, you can do all this math on your own. I am old and feeble, yet I can multiply 4 times 0.25 and understand that that's 1, right? Because 0.25 is a quarter, and 4 times a quarter has got to be 1. And 1 times 1,000 is just 1,000. And 40 squared can be done as easily as 4 squared, so 16, plus a couple extra zeros. You should be able to do all of these things. You are smart, smart people. And I wouldn't stop here, because this is 40 plus or minus the square root of 600 over 0.5. And you should probably in your head know pretty close what the square root of 600 is, because 25 squared is 625. So I would assume the square root of 600 is like 24, right? Maybe 23 or maybe 24 and a half. It's 24 and a half. So this equals 40 plus or minus, and I'm just going to put 25 because I don't want to write 24 and a half. You guys have, at this point, this might be the point where you use a calculator. And if you want to put 24 and a half because it makes you feel better and you feel like you're being somehow exact, which you're not, let's just do that. 24.5 plus 40 is 64.5 over 0.5. And 40 minus 24.5 is 15.5 over 0.5. And now that we're all the way there, divided by 0.5 is multiplying by 2. So 129 seconds and 31 seconds. Those are my two t's. No calculator needed, folks. If an old feeble guy like me can do it, you young, smart whippersnappers can probably. Get away from your calculators, all right? On the AP exam, yeah, use them. But at home, I bet you spend as many time punching it into your calculator again and again and again and getting different answers all the time. Was any of this particularly hard to do? I would encourage you. Which answer's right? 31, yeah. What happened to, oh yeah, there it is. It's gotta be 31. And the reason is simple. There's two answers because we asked when the two trains would be at the same position. Now, the lower time is when they meet first. And if they crash, there'll be no other position. Thus, 31 seconds is the right answer. Go back now and find out where that is. Why is there a second answer? Take the trains and put them on parallel tracks, not the same track. And what would have happened? This one, not slowing down. This one, slowing down, turning around, and coming back, and they meet back up. That's why there's a second answer. The other one that's slowing down will eventually stop, turn around, and come back and meet the other one if given a long enough time. Apparently, an extra 100 seconds will be enough. That's why there's two answers. Now, again, this isn't actually the answer. If you want the answer, you need to use this correctly. I'd say there is the right place to go. It will tell you where this is. 20 times 30 is like, what, 600? So, or 620. So the position is about 620 meters. That's where that is. So that'd be from the origin, positive 620 meters. I'm not sure what else you're supposed to do with that, but that's enough.